announce João Paulo Almeida, that will present his talk entitled "A Hotline Game on Networks."
So good morning to you all. Thank you very much, Bruno. Thank you very much for the invitation. It's a pleasure to be here at the national meeting of the Portuguese Mathematical Society. I will present my talk, The Hotline Game on Networks. I'll give some introduction on the Hotlink model, then I will expand the Hotlink model to what we call the Hotlink town model and give some insight on the Hotlink town model with uncertainty on the production, on the firm's production costs. So to start with, in 1929, Harold Hotlink published a seminal paper called Stability in Competition. And this seminal paper had the greatest impact and influence in the research on what we call special competition or location theory. In economics, special competition is concerned with the location interdependence among economic agents under imperfect competition. In the original Hotlink model, two firms are the players of what we call a two-stage location price game. In this two-stage location price game, first firms choose their location and then they set their prices. The goal is to study the location and price strategy that maximize the profit of each of the competing firms. Okay. So in his analysis, Hotlink presented a village characterized by what he called a main street. And this main street is represented by a line segment where a uniformly distributed continuum of consumers buy a homogeneous good or commodity in one of the two firms of the village. Consumers have no preference on any of the firms and face linear transportation costs when buying in one of the two firms of the village. Hotlink concluded that the firms would eventually agglomerate at the center of the line, side by side, and split the market into two separate regions. And this observation is referred to as the principle of minimum differentiation. 50 years later, Das Brumon and his co-authors showed that this principle of minimum differentiation is in fact invalid, since there is no price equilibrium solution for all possible locations of the firms, in particular when they are not far enough from each other. So this is the original Hotlink model, the line, the firm A and firm B. We set them up here at the endpoints of this line. Line has length L. The consumers are uniformly distributed into this line, and these two firms, they sell the same commodity at unitary prices PA and PB, and they face unitary production costs CA and CB. So in this model, no customer has any preference for either firm except on the ground of the price plus the transportation costs, which is T per unit of length. So we assume that each consumer buys a single unit of the commodity in each unit of time and in each unit of length of the line. There is what we call a point of division X, depending on the prices practiced by firm A and firm B, to whom it is a matter of difference whether if he goes to firm A or to firm B to buy the commodity. So this means that the expenditure that the consumer faces is the same, and to define or to compute this consumer, the position of this consumer, we just equal the expenditure. So the expenditure of the consumer, if he wants to come to firm A, it will be the price practiced by A times the transportation costs times the distance from A. Exactly the same for going to buy to firm B. Okay, so in this solving this equation for X, we identify exactly the position of this indifferent consumer. In this model, we assume that both firms have a non-empty market share. This means that this consumer is in the interior of the line. So assuming that both firms A and B have a non-empty demand, the profits can be given by the usual formula, price minus cost times market, and computing using the second order conditions, we can compute the optimal prices that firm A and firm B should practice, which are given by these two expressions. So the pair of prices, PA and PB, is what we call a local strategic optimum equilibrium if the indifferent consumer satisfies this condition here. The Hotelling model, we say that satisfies the bounded cost condition if the difference between the two costs is less than 3 TL. So this condition here is equivalent to the bound condition costs. We obtain that the following result: under the bounded condition costs, the pair of prices is in fact a local strategic optimum equilibrium. Okay, so now passing to this model, to the network, we introduce what we call the Hotelling town model. So we extend the Hotelling model from the line to the network. And we try to mimic a real town. In this mimic exercise, the roads of the town are the edges of the network, the crossroads are the vertices with degree higher than 2, and the ends of no exit rows are the vertices with degree 1. Firms are spread all over the town, and the consumers are uniformly distributed along the roads. The roads can have different lengths. This means different market sizes for the firms, and the firms can have different production costs, which gives us the firm's heterogeneity. In this model, it is different from usual network games because consumers are assumed to be uniformly distributed along the edges of the network and not at the nodes as usually are in these network games. A price strategy is a vector where the coordinates are the commodity selling prices of each firm, and is, as in the original Hotelling model, the expenditure of a consumer that chooses to buy into a firm inside the network consists in the sum of the price practiced by that firm plus the transportation costs, that it is proportional to the minimal distance inside the network from his house and the firm. So again, the firms compete in a two-stage location price game. First stage, firms choose their location. Second stage, firms choose their prices. The goal again is to study the location and price strategy that maximize the profit of the competing firms. In the price sum game, the main goal is to compute the price strategy that has the following two essential economic properties. It is a local strategic optimum, so meaning that any small deviation of a price of a firm provokes the decrease in its own profit. And it has local market structure, so all firms have non-empty market. The first property stabilizes the prices because no firm has an incentive to do small changes in their prices. And the second property stabilizes the set of competing firms because every firm has non-empty market. So using a sufficiently high entry cost, no firms enter or leave the market. We call a price strategy satisfying these two properties, a local market optimum price strategy. So we introduce what we call the weak bound cost condition. This condition is on the exogenous parameters of the model and gives a bound in terms of the transportation costs and a minimal road length on the maximum difference between the production costs and on the maximum difference between road lengths respectively. Under this weak bound condition costs, we prove that the price subgame has a local market optimum price strategy. Furthermore, the local market optimum price strategy is unique. And an observation regarding the point from Aspromont is that under this weak bound condition, cost condition, the firms cannot be located too close. So their objection to the existence of a local market optimum price equilibrium does not apply. For the local market optimum price strategy, we present an explicit closed formula and an explicit series expansion formula. The closed and series expansion formulas exhibit explicitly how the local market optimum price strategies of the firm depends on the production costs, on road market sizes, and on firm locations. So the static analysis of relevant economic quantities can be done rigorously. So assuming that the firms may not know the entire network, we say that the firm has an n-space bounded information if the firm knows the network structure up to n rows from its location. This knowledge is about in terms of production costs, node degrees, and road sizes. So we prove that the firm with n-space bounded information is able to compute an n-approximation price with the property that the n-approximation price converges to the local market optimum price exponentially fast with n. So the influence of a firm in the local market optimum price strategy of other firms decreases exponentially fast with the distance between these two firms. Yet, a local market optimum price strategy may not be a Nash equilibrium price. So for that, we introduce what we call the strong bound condition that in comparison with the weak bound condition has the additional feature of its bound to depend also on the maximum node degree of the network. Under this strong bound condition, we prove that the local market optimum price strategy is in fact a nice Nash price equilibrium strategy. In the location subgame, we consider that the location for the firms is admissible if it satisfies the weak bound condition, and we assume that firms, after choosing an admissible location, will practice the local market optimum price strategy. So similarly to the original Hotelling model, in the line, we prove that the firms located at the ends of no exit roads have an incentive to deviate from their location, so they go inside the road. However, firms located at crossroads do not have incentive to deviate from the location. In this sense, firms prefer maximum differentiation in contrast with the original Hotelling model in the line. So we know that this result has some empirical evidence because in real towns, shops are usually located at crossroads. So in the price subgame, technical details, the Hotelling network consists of a group of roads, which are the edges of the network. Consumers live and are uniformly distributed along these edges, and a group of firms that are in the nodes of the network. So we start with the firms located at the position in a neighborhood at any vertex, at some vertex, their corresponding vertex. And every road has two vertices. And also in a neighborhood of every vertex is located a single firm. So consumers can buy one unit of commodity in any firm of the town. And firms compete in prices a la Hotelling in the network. So the firm has unit cost CI, charges the same unit price PI to all its customers. The road Rij has length Lij, and consumers are uniformly distributed along the road. Ni is the set of all neighboring vertices for which there is a road connecting the vertices, and the cardinal is the degree of the node I. Tilde Ij will be the distance between the location of the firms Fi and Fj, and epsilon is the maximum deviation between the node I and the location of the firm Fi. So for every road Rij, the length of the road Lij is close to the distance between the two firms Fi and Fj. A price strategy consists in a vector whose coordinates are the competitive prices of each firm. A consumer located at the point X of the network who decides to buy at firm Fi spends exactly the price practiced by the firm I plus the T times the distance inside the network from the location of X to the firm I. So given a price strategy, the consumer will choose to buy in the firm that minimizes his expenditure. The market consists of all consumers who minimize their expenditures by choosing to buy in firm Fi. The market size will be the Lebesgue measure of the market. The profit is exactly the same, price minus costs multiplied by the market. and the local firms of a consumer located at some point in some roads with vertices I and j are considered to be Fi and Fj. So a price strategy determines a local market structure if every consumer buys from one of his local firms. If a price strategy determines a local price market structure, then for every road, there is one consumer located at the point Xij to whom is indifferent to buy from firm I or firm J. So equals this expenditure, and thence the profit of the firms of firm I is given by this formula. So to define the bound length and cost condition, let us consider the K capital M, the maximum node degree of the whole Hotlink town, C capital M, the maximum production cost of the whole Hotlink town, and C lower M to be the minimum production cost of the Hotlink town. So we define this delta, this amplitude of the cost to be the maximum cost minus the minimum cost. So similarly, we define the delta L as the maximum road length of the Hotlink town minus the minimum road length of the Hotlink town. So with these definitions, we define what we call the weak bound length and cost condition. If the sum of delta C minus T delta L is less than this value here. So the Hotlink town admissible market size is the vector whose coordinates are the admissible local firm market sizes given by these coordinates. And the neighboring market structure K will be a matrix whose coordinates will be the inverse of the node degree I when you have a road Rij between firms Fi and Fj, and 0 if you do not have a road connecting firms Fi and the firms Fj. So our theorem, if the Hotlink town satisfies the weak bound condition, there is a unique local optimum price strategy given by this closed formula and this expansion formula here, this series expansion formula. Here, one is the identity matrix. To ensure a Nash equilibrium price strategy, we need to define the strong bound cost and length and cost condition, and this is given by if the deltas delta C plus T delta L are less than this expression here. So if these deltas is verified, there is the strong bound length and cost condition. And if a Hotlink town satisfies the strong bound condition, then there is a unique Hotlink town that is Nash equilibrium price strategy. So the Nash equilibrium price strategy for the Hotlink town satisfying the strong bound condition determines a local market structure, which means that every consumer located at some road Rij spends less by shopping at his local firms and than in any other firm of the town. So the consumer will buy either at firm Fi or firm Fj, which are the local firms for this consumer. For the node degree, the location subgame, let us see how the profit of the firm depends on the distance between its location and the corresponding node. So we say that the firm is node local stable if the profit of this firm being exactly at the node, it will be bigger than if he deviates a bit from the nodes. A Hotlink network is node local stable if every firm in the network is node local stable. So let us define this matrix Kij by the coordinates Kij, which are this expansion regarding the degrees of the nodes, the degrees of the nodes in the Hotlink row, in the Hotlink town, and the weighted balance that gives some symmetry on the markets in regarding related to every node. Our theorem, firms with node degree Ki equal to 1 are node local and stable, so they tend to come inside the edge. They don't want to be in the node. firms with node degree equal to 2 are node local and stable, except for networks with 0 weighted balance. That means that the market is balanced between from the left and the right to the node. Firms with node degree 3, whose neighboring firms have nodes degree greater or equal to 3, are node local stable. And firms with node degree Ki bigger than 4, whose neighboring firms have nodes degree greater or equal to 2, are node local stable. So if the minimum node degree of the hotlink town is bigger than 3, and the hotlink town satisfies the weak bound condition, then we have that all firms are node local stable. And I think I have passed my 15 minutes, so I will finish with this theorem. Thank you very much for your attention, and I would like to see or to hear about your comments and questions.
Thank you, João Paulo. I'll open the floor to questions. You can use the Q&A button to make some questions, but I'll open the hostilities, let's call it this way. I was wondering about a different model. Would it be possible to make something that is a continuum plane where firms are at some locations, or is it very far away from what you are doing?
I'm sorry, I didn't understand. What do you mean by a continuum plane?
To assume that the consumers are in a plane instead of in a line.
The consumers are in the
plane. In the plane.
Ah, okay, plane. Okay, I understood. Well, this is a network. So in fact, we are mimicking the town. And when you have a plane, if you the possible directions that meaning that when you are in a network, you will have a finite number of firms. Okay, and when you have a plane, there is no limit. So all firms, the firm will compete with like an infinite number of firms, and we are not doing nothing on that. Here, the idea is that there is a connection between two firms. It is connected by the market, okay? And they try to fight on the market of that specific line. If you open it to a plane, I don't know, it will be, you add a new dimension, I don't know, I think it is maybe very interesting, but I do not have an idea how to attack this problem with like an infinite number of directions possible. I don't know, I have to think about it, but no, we really connect through lines, so it is one-dimensional, not two-dimensional.
So I was wondering that because it's quite a different problem. I'm not sure if it's solvable this way. But that came from the bounded conditions that you talked about.
Yes.
And that restricts consumers to buying at a firm 2 steps away.
Yes, local firms, but you have to think local firms inside one direction. If you open to a plane, what is exactly it will be like a vicinity of the, and I don't know. It is a whole different perspective, I think.
Yeah. Okay. So, since we don't have any further questions, let me thank João Paulo Almeida for his talk, and we'll pass to the next speaker, which will be Filipe Martins, that will talk about adaptive dynamics for the Baliga-Maskin model of contribution for a public common good.
Okay, let me just share, check if I can share my screen. Okay. May I start?
Yes, please.
Thank you. So this work is called Adaptive Dynamics of the Baliga-Maskin model of contribution for a public or common good. This is based on joint works and an ongoing work with Elvio Accinelli and Alberto Pinto. So this is a structure of the talk. I will first give a short economic motivation and introduction, then I will describe the model, and I will introduce dynamics, followed by the discussion of the basics of attraction of the equilibrium of the model, which are the main results of that I want to present here, because we are able to fully characterize the basis of attraction, and then some short conclusions. So the motivation is the following. The motivation comes from economics. So first, what is a common or public good? Common or public goods in economics have the following property of being non-excludable, which means that it is not possible to exclude consumption or use by other agents or individuals in an efficient way. So you may try to restrict their consumption, but you are not able to fully exclude them from such consumption, even if they do not contribute to the good, or even if they do not pay. So then, adding to those non-excludable characteristics of common and public goods, there are also another feature that are normally non-excludable externalities associated with such goods. Well, in economics, an externality is a negative or positive effect that occurs to a third party that is not involved in the initial economic transaction. And so it is non-excludable because these externalities, these external effects to such third parties will affect everyone, and it's not again possible to exclude them from feeling the effects of such externalities. The common examples are negative externalities, which include the exhaustion of fish or coal stocks and sea pollution. They are non-excludable because they affect everyone, and it's not possible to exclude them from feeling the effects of such externalities. And the last observation is that non-excludability is normally associated with the occurrence of free-riding behavior, since individuals that do not pay for such a good or do not contribute to its provision will not be excluded from its using because of the non-excludable property. Okay. Now a short literature review based on a paper from the Massey from 2003. They propose a model of contribution for a good such as air, where there is a non-excludable externality, that is air pollution. So the good associated that they study in this context is, so we have a negative externality, common public externality, non-excludable, which is pollution, and the good itself is pollution reduction. And what they obtain is that in the case of no agreement between the agents involved, they will resort to individual actions that consists of only one contributing agent, while the other agents free ride on this kind of behavior by this. So one agent contributes, and the other ones take advantage from that contribution from that agent. So it is a free riding behavior. And the authors argue that the consumption and provision of the non-excludable good, that an external mechanism might be necessary to ensure an efficient, socially efficient Pareto outcome. Pareto in this case, normally in the economics literature, Pareto efficient outcome means saying that we have a kind of socially efficient outcome, which is not the case in the case of free riding behavior. So what we will do is introduce an adaptive dynamics for this model. Adaptive dynamics also means a myopic dynamics, because agents adjust their strategies to the local best direction to increase their utility. And we'll show that the equilibrium that corresponds to that agent contributing and the others free riding on it is asymptotically stable for dynamics, and after that we will also show that is generically globally stable for dynamics, even if there are some periods where other agents increase their contribution. So what we obtain is a kind of dynamical version of Baldig and Manskin's argument for the need of some mechanism to lead to the Pareto optimal outcome. And we will discuss what we mean by some mechanism in the conclusions again. So now the model, there are n players indexed by I, 1 to n, then they have individual contributions which we denote by Rj, which are non-negative, individual contributions for the good, and we have the aggregate contribution, which is a sum of each of the individual contributions, which will be very important in the analysis that we're going to make. Sometimes we shall make use of this notation, which is usual in game theory. So R minus I, all the agents except, so it is the collection of all the individual contributions except agent I. And in the context of Baldig and Maskin, these are contributions for a common good, which is reduction of air pollution. So in a broader context, the model may be interpreted as saying that these are contributions or efforts for a certain common or public good that is not necessarily the reduction of air pollution. And we are going to consider, and this is the first generalization that we do from the original Baldig and Maskin model, we are going to consider utility functions which have this form here. So we have a first term which we call the gross benefit of the aggregate contributions for the good, and then we have a cost which is a linear function, and beta I is the marginal cost. So this is a kind of usual utility function in economics. It's called a quasi-linear utility function because we have a linear part on the cost and the non-linearities are on the gross benefit, which depends on R, on the aggregate contribution. Normally, we also assume that these functions UI are strictly concave. That's the usual assumption in economics. We are also going to do it. So we denote by W the derivative of the gross benefit. So we obtain the marginal benefits for community I. And as usual in economics literature, we are going to assume that these functions UI are strictly concave, which means that the W functions are strictly decreasing. And so we obtain the marginal utility, which is the difference between this marginal benefit minus the marginal cost, which is just beta I. The second assumption that we are going to do, and which is also very usual in economics, in mathematical economics, is this one. We assume that the marginal utilities satisfy these limit conditions. So when we go to infinity, we get a negative value on this side, and we are going to 0, we get a positive value. So these conditions are also very usual because there is in economics, there are a set of conditions which are called Inada conditions or Inada type conditions, which imply this condition that we are going to use here. So the assumptions that we do are relatively standard among the economics literature, the mathematical economics literature. So it was just an observation. These conditions are implied by the usual another type condition on the gross benefits UI, which say that the derivative is such that UI 0 is plus infinity and the limit when we are going to infinity is 0. So these are the two main assumptions. So quasi-linear utility function with some strict concavity on the benefit function and then the another type conditions. So these assumptions imply that the functions Vi have a 0, which is unique since Vi is decreasing. We are going to denote it by Ri with a bar. So this function is 0 at that point. We call it the optimal contribution or threshold contribution level of agent I. For simplicity of notation, after a permutation of agents, we can order them in this way, just to make the analysis easier. And the example, so this was based, this extension and this generalization was based on Balding and Masking model. So one example is what we call the generalized Balding and Masking model, which is utility functions of this kind. So each player has a preference or valuation theta I for good. In that case, the preference for air cleaning or air pollution reduction. Then there are alpha i's, which represent some kind of intensity or power of the utility gains from the aggregate contributions for the good, r to the power alpha I. The marginal cost pi. The marginal utility is given by this formula, and the ultimate contributions levels are given by this formula here. And the Balding and Masking model that is present on that paper that I have mentioned before consists of making or considering unitary costs, beta I equal to 1 for every agent, and considering alpha I equal to 1 alpha. So we have a square root of the aggregate of contribution. So this is a small generalization of the Balding and Masking model, because we introduce these parameters alpha and beta, and after that we have generalized also to the previous context, which we just consider some abstract utility functions given by U or by the gross benefit UI. So we are going to generalize results to this context, which includes the generalized Balding and Masking model. So just again, small motivation is that what happens in the Balding and Masking static optimization, and it also happens if you consider alpha, not necessarily alpha equal to 1 half, so you can consider alpha in the interval 0 to 1. And what happens is that if we repeat the Balding and Masking static optimization argument, what happens is that in the case of no agreement, agents maximize individually. The solution of the maximization program is given by this expression here. If the theta, which is the contribution of the agent, the preference of the agent for the good is maximum and 0 otherwise. So the total contribution in this situation is this one. So what we have is really the agent with a maximum theta contributing, and the other ones contribute 0, which means that they are free riding on agent with a maximum preference for the good. And taking this in mind, we are going to see that we obtain some, in the dynamical framework, we obtain some more or less the same problem in the dynamical framework. So, which in the end will mean that this problem will need to be addressed at a dynamical level as well, if we want to try to solve. So the myopic dynamics or adaptive dynamics are of this kind. So we have the time derivative of an individual contribution is equal to the Ri times, sorry, that's a mistake there, it's Vi. So which means that the relative rate of change of Ri, which is Ri dot over Ri, is given precisely by the marginal utility of the individuals. So this is again usual in economics and in evolutionary theory and evolutionary game theory. So Vj minus, so sorry, I made a mistake here. It's not, this Vj equals 0 as a unique solution, which we have seen is equal to R equal to the threshold level Rj, aggregated effort that maximizes J's utility. And we have called it before the threshold aggregated contribution, optimal contribution level. Another good word to describe it is subsistence aggregate contribution level, because if we are below this threshold, then the marginal utility is positive, so that the derivative will be positive, and the agent I will want to increase his contribution because he's below that target level. And if he's above the target level, the marginal utility is negative, the derivative is negative and we want to decrease this contribution. So the equilibrium of the system are given by zero contribution equilibrium, where no agent contributes, the free riding equilibrium, which are similar to the ones that I've described in the static framework of Balding and Maskin, which are of this kind. So no one contributes except agent. Sorry, again, I changed some. That's I. So only the agent I contributes with this threshold level. The others are free riders, and this happens on the case where there is a strict difference between the thresholds. And there are also some kind of low cooperation equilibrium, which is a limited form of cooperation, because there are some agents, a group of agents, which contribute for the good. And this occurs in the case where their thresholds are the same, are all the same, and there is what happens in this case is that the aggregate contribution R, which is the sum of all these values here, they just sum, and their sum is equal to the threshold level, which is common to each of the agents. So this is a kind of low cooperation equilibrium because there's a kind of limited cooperation. These agents share among themselves cooperation for good. Now, the main part of this is the stability. The zero contribution equilibrium is always a repelling fixed point for dynamics, since every community or agent would prefer to increase their utility by increasing its contribution. So the 0 point is done. Then the free riding equilibrium of this kind, which is similar to the Balding and Maskin. So if we compute the linearization of the dynamical system at this point, we see that in this case we obtain the following eigenvalues. So we have these eigenvalues which are negative, then we have this from I plus 1 till n which are positive, and then we obtain always this eigenvalue omega, which is always negative. So the consequence of this is that this equilibrium of this kind, free riding equilibrium, are saddle points, and the only one that is possibly not a saddle point is Rn, the free riding equilibrium corresponding to n, the agent n. And recall that agent n, according to a previous assumption, was the agent with the highest threshold. So we can see it as the one which with the highest preference for the good, because he's the agent that has a higher optimal contribution level, or threshold contribution, or subsistence contribution level. So it is the one that needs to attain a higher aggregate level in order to be satisfied, because of this interpretation that I've given here. So, and this one, in this case of n, if we put I equal to n, what we obtain is that all these eigenvalues will be, so there will be no eigenvalues in this set. So they will, all the eigenvalues will be negative, so this point will be locally stable. So what I explained, the equilibrium where the only contributing agent is the one with the greatest optimal contribution level for the group. So this is the first part that we have done. In the beginning, we did not focus much attention on the low cooperation equilibrium, but after that, with some more refined analysis, we also noticed that we were able to characterize the basins of attraction of the equilibrium, and we are also able to characterize the basin of attraction of the low cooperation equilibrium. So the first observation is that the low cooperation equilibrium is a kind of a hyperplane of equilibrium, because we just have that this sum needs to equal the threshold level I. Now I will explain how we obtain the characterization of the basins of attraction, and the first we do, and the most important, is to make an analysis of the dynamics of the aggregate contribution R. And one of the main formulas that we obtain is that we can make a decomposition of the derivative of the aggregate contribution R with respect to time in this form, which has the property that in the first group, these marginalitudes are negative. In the second group, the marginalitudes are non-negative, and with equality only when J equals I plus 1 and the aggregate contribution equals precisely one of the thresholds. And this formula allow us to characterize and to get some properties of the aggregate contribution R. So, and the first thing that we are able to obtain, it's kind of a lemma, a very important lemma in our that we obtain in our analysis, is that using this, we are able to obtain that the function that R, the aggregate contribution as a function of time, has no local maximum. So the conclusion is that the function R, the aggregate contribution, is either strictly increasing, maybe constant, in which case it corresponds to a dynamical equilibrium of the system, may have a unique global minimum after which it is strictly increasing, and the last possibility is that it is strictly decreasing. So we have ruled out some kind of more strange behavior, and taking this into account, we are able to prove and to characterize the basis of attraction of the equilibrium. So just to explain what we do is we first consider initial condition such that the individual contribution of agent I is greater than 0, and every agent after I, which means with the preference for the group higher than I, is initially 0. So it will be 0 for all time. And this kind of forms that the function R takes. The first step, we conclude that the monotonicity and boundedness of the function R, given by the previous possibilities for the function R, imply that it converges to a limit, to a certain limit. After that, we are able to prove that that limit must be lesser or equal than Ri. And after that, we will conclude that it is indeed equal to Ri, and all the individual contributions of the other agents except the I agent converge to 0, which means that Rk t goes to 0 for k less than I. So the idea is that what will happen is that the individual contribution will converge to the aggregate contribution, and so the individual contribution converges to the I threshold Ri bar, and with all the other agents efforts converging to 0. And hence we have the dynamics converges towards the free riding equilibrium Ri. So this is the idea, and the theorem that to obtain is this: the Base-Inhofe direction of the free riding equilibrium consists of all initial conditions such that Ri is different from 0 and Rj is 0 to all the agents with the highest preference. In particular, for I, when I equals n, the Base-Inhofe attraction of this equilibrium consists of all initial conditions such that the highest agent n is initially contributing a non-zero as an initial non-zero contribution, and the same structure of the proof that I have described, the same sort of argument, also allows us to characterize the Base-Inhofe attraction of that hyperplane of limited cooperation equilibrium, and the conclusion is very similar. The union of basins of all low cooperation equilibrium of a given type consists of initial conditions such that one of agents that is in that group of contributing agent has a non-zero contribution, and all the agents which have a strictly higher preference for the good, which means J2 greater than I plus K, they contribute 0 initially. So we have a characterization of the Bayesian of direction of that hyperplane of equilibrium. We are not able to characterize exactly the Bayesian of attraction of a specific equilibrium on that hyperplane of low cooperation equilibrium. In some situations we can, which is what happens if the marginal utilities between that group of agents is the same. In that case, because of this expression, we have that we obtain 0 on the right hand side, and since we obtain 0, so this proportion remains constant, and since the proportion remain constant, we have a full the Bayesian of attraction of a given low cooperation equilibrium on that hyperplane of equilibrium is completely determined from these proportions. So in this case, with of equal marginal utilities, we are able to obtain that. Just a figure to illustrate what happens in the case of the Baligan mask utility functions. So we consider alpha equal to 0.75, 3 agents with different contributions for the good. All the marginal costs are all equal to 1. And what we obtain is that, as expected, as time increases, the highest agent, which is plotted in purple, which is R3, it approaches the aggregate level, which is in purple. The observation that is important in this case is that so the R1 initially decreases its contribution to 0 immediately, but there is a moment where the threshold level, the aggregate level R is too low even for agent 2. That's why initially the agent 2 increases its contribution. It increases its individual contribution because its threshold level, its subsistence level, which is R2 bar, is not attained from so the aggregate contribution is below that threshold level. So there is a period where it needs to increase its contribution, and then R3, which is the highest agent, takes over, and in that period what we see is that R2 starts to behave as a free rider on R3, and in the long term that's what happens. So this is the economic interpretation of the results. So this is the conclusion that I have already described, and what we obtain. And so what we do is we dynamically reassert Baligan-Massin's argument that to ensure variety efficient outcome, some external mechanism might be necessary, and there are several possibilities, and one of that we are possibly going to explore in the future is the possibility of the formation of cost-sharing coalitions of agents contributing for the public good. This will need to be made on a static framework, but also taking care of dynamical incentives, because as we have seen, dynamically the equilibrium is also stable. So we have to address the problem in different frameworks to ensure that in an evolutionary way, given by the dynamics, that those cooperation equilibrium might be stable. So these were my conclusions. Thank you very much. The references are this. This is the first paper that we published on the subject, and we have a submitted paper about the Bayesian of attraction, and this is the original paper by Valley and Mask. Okay, thank you.
Thank you, Philippe. And in the interest of time, and since there are no questions, I will pass immediately to the next speaker, which is José Martins, that will talk about periodic vaccination strategies in the basic reinfection city model, which vaccination strategies seems to be in order in terms of the COVID pandemic, although it's not the focus of the paper. Okay, so the stage is yours.
Thank you, Bruno. Definitely, I will not bring COVID-19 to this talk, but is something that could and should be, of course, applied to these nowadays problems. Okay, so thank you very much. I would like to thank the organizers for the opportunity to present here our work. This is a joint work with Professor Alberto Pinto. It's a very simple and, in my opinion, very nice application of game theory. We try to understand, we try to study people behavior with respect to vaccination, basically. The summary of my talk is here. I will give a very brief introduction. Then I will define the vaccination strategies, typically what is best for people. In the third point, I will introduce the epidemic model that we consider, not the COVID-19 model, of course, but it's a very simple and very interesting model. And to finish, I will talk about the evolutionary dynamics of the strategies. Okay, first, to start, I have to say that this study only applies to diseases where vaccination is voluntary. Okay, people must have the option to decide if they want to be vaccinated or not. Okay, and if people have that option, then several things should be taken into account when people decide to take the vaccine or not. One of those things is the probability of becoming infected. Okay, if this probability is too small, people may not be interested in the vaccine. Okay, but if the probability of becoming infected is high, people would be interested in the vaccine, okay, to avoid the infection. Other things that people take into account in the decision moment is the morbidity risks. Okay, the morbidity risks are the adverse consequences that might result. Okay, and if these adverse consequences from the infection are quite severe, people would be interested in the vaccine. Okay, would be interested in avoid the disease. Okay, but on the other hand, if the adverse consequences from the vaccine are also severe, there are several side effects that the vaccines may have, then people may lose their interest in the vaccines. Okay, so there are different things that people take into account when they choose between being vaccinated or not. Okay, also the decision of each individual is influenced by the decision of all the others. Okay, basically this is the idea. If everybody else takes the vaccine, I don't need to do it. Okay, everybody is vaccinated, the disease will disappear sooner or later, and then I don't need to take the vaccine. Okay, so this is again theoretical problem, and we study here the evolution of the individual's decisions when these morbidity risks evolve over time. To formulate the problem, I have to introduce some notation. The strategies, first, the capital P is the individual strategy. Basically, we can think on this as the probability that an individual will choose to take the vaccine. The small p is the population strategy. Okay, the small p basically means the proportion of the individuals in the population that decide to be vaccinated. Okay, the R is the morbidity risk. We have two different R's, RV, which measures morbidity risks from the vaccine, and RI, the morbidity risks from the infection. Okay, and we will use the ratio between these two, which we call the relative risk. Okay, the pi is the probability of being infected. Okay, the pi v bar is the probability that a non-vaccinated individual will eventually become infected, okay, for a certain proportion of the individuals in the population vaccinated. And the pi v is the probability that a vaccinated individual will eventually become infected, okay? The vaccines, we all know that are not 100% effective. So even vaccinated people may be infected again, okay? And this function measure that probability. We define the difference between these two probabilities as the vaccination infection risk index, okay? This function probably is one of the most important quantities in our study, okay? It is this risk index that will define what is best for each individual, if it is to take the vaccine or not, basically. Sorry. The payoffs to the non-vaccinated and the vaccinated individuals, we define it this way. To a non-vaccinated individual is minus the morbidity risks of the infection times the probability of that non-vaccinated individual become infected, okay? It is negative because the payoff will decrease with the morbidity risks, okay? The payoff to the vaccinated individuals is minus the morbidity risk of the vaccine minus the morbidity risk of the infection times the probability of that vaccinated individual will eventually become infected, okay? With these two payoffs, we can compute the vaccination expected payoff, which is simply the mean value of these two quantities, okay? The payoff to the vaccinated times the probability of being vaccinated, and the payoff of the non-vaccinated times the probability of not being vaccinated, okay? And we rescale this expected payoff just to write it in terms of the relative risk, okay? Now, we can define the best strategies or the strategies that are more likely to be adopted, okay? And we start by the vaccination Nash equilibrium, okay? We can say that P star is a vaccination Nash equilibrium if no single individual has an incentive to deviate his or her strategy from that Nash equilibrium. Okay, so we start to assume that all individuals in the population vaccinate with that strategy, with that probability. And if anyone changes from that P star strategy to a different one, it will always obtain the same or a lower payoff. So this difference is 0 or negative, okay? And to find the Nash vaccination equilibrium, we have here a very simple problem, which is to study this sign of this product, okay? So our first result is quite simple. We have 3 different Nash equilibrium, okay? The pure strategies where no one takes the vaccine, and the pure strategy where every individual in the population choose to be vaccinated, okay? The 0 probability appears if the relative risk is too high, basically, greater or equal than the risk index when nobody in the population takes the vaccine. And the other case, all the individuals take the vaccine if this relative risk is too small, okay? In between these two vaccination strategies, we have a mixed vaccination Nash equilibrium that is a certain probability, it is a certain probability between 0 and 1, such that the relative risk is equal to the risk index function in that Nash equilibrium, okay? So we fully characterize the vaccination Nash equilibrium for the expected payoff that we defined. To define different vaccination equilibrium, we start to assume the following. All individuals in the population are vaccinating with a certain probability P, but a proportion epsilon of individuals change from that strategy to a different one, to a Q strategy. Okay, so we have a new population vaccination strategy. We can compute the expected payoff of those that change to the new strategy. We can compute the expected payoff for those that remain in the original strategy. And the difference between these two payoffs is the function that measures the gain that individuals have to change their vaccination strategy. Okay, so this difference is the expected payoff gain function. It measures the incentive that a small group of individuals has to change their vaccination strategy. An evolutionary stable vaccination strategy is a P-star vaccination strategy, a certain probability P-star, if any small group of individuals that try to change the vaccination strategy from P-star to a different one will always obtain a lower payoff. So the payoff gain function that measures the expected payoff, the gain of moving from P-star to a different strategy is strictly negative. Okay, in these conditions, P-star is what we call an evolutionary stable vaccination strategy. And to find this type of equilibrium, we have similar conditions to the Nash equilibrium, okay? But for the pure strategies 0 and 1, the inequalities become strict inequalities, okay? And the most important difference is for the mixed strategy that keeps the same, okay? The relative risk must be equal to the risk index in the evolutionary stable vaccination strategy, but we have now an additional condition that states that the risk index function must be a strictly decreasing function, okay, in the neighborhood of the evolutionary stable vaccination strategy. If it is not a strictly decreasing function, we have a simple Nash equilibrium. Okay, to apply all these results, all this framework, we consider the simple reinfection model, the basic SIRI model. We have three classes of individuals: the susceptibles, the infected, and the recovered. Okay, we have a first infection transition from the susceptibles to the infected. We have a recovery transition from the infected to the recovered. Okay, we already choose a time scale that put this transition rate equal to 1. Okay, and we have here the novelty, the important thing that this model comprises, which is the possibility of reinfection. Okay, the recovered individuals might be infected again. Okay, the R0 that appears here is the basic reproductive ratio. Okay, the sigma parameter measures basically the intensity of the reinfection when compared with the first infection. Okay, the sigma is the ratio between the reinfection rate and the first infection rate. So it's typically smaller than 1. Okay, in our simulations, we will put this ratio equal to 1/4, which means that the first infection is 4 times stronger than the reinfection rate. Okay, the vaccination, we introduce it in our model in this transition from the susceptibles to the recovered. Okay, we assume that a certain proportion P of the susceptibles goes directly to the recovered by vaccination, okay, by taking the vaccine. So we identify the susceptibles as the non-vaccinated individuals and the recovered as the vaccinated individuals. Okay, this is a huge or a big simplification, recovered and vaccinated means the same in our model. Okay, it's not properly the best thing that we can do, but it's also something that makes sense. Okay, nowadays being vaccinated or being recovered is not the same, but it's somehow similar. Okay, so we consider a very simple model that should be, of course, improved, but is also quite interesting. To present the results for this SIR-I model, I need to distinguish two different cases. The case of a small basic reproductive ratio. In our simulations, small means that is less than 2 or something quite close to 2. And the case of large basic reproductive ratios, okay? In the small part, in the small values, we have a very defined, a very simple vaccination scenario, okay? The unique and well-defined equilibrium. But for large basic reproductive ratios, we have some more complexity. We have more than one vaccination scenario. Okay, so the first case, in our simulation, I did this graph for basic reproductive ratio equal to 1.5. So it's a small value, it's less than 2. And here we have two different cases, basically. If the relative risk is too high, then the Nash equilibrium is 0, okay? It is indeed an evolutionary stable vaccination equilibrium. And in this case, nobody takes the vaccine, okay? But on the other hand, if the relative risk is not too high, we have a positive evolutionary stable vaccination scenario. Positive vaccination strategy, and some proportion of the population, a certain amount of individuals will take the vaccine, okay? For large basic reproductive ratios greater than 2, we have different results. If the relative risk is quite high, once more, the evolutionary stable vaccination strategy is 0. Okay, and nobody will take the vaccine. But if the relative risk is not too high, in our simulation is less than 0.33, more or less 0.33, then we have a high, what we call a high vaccination scenario, where the vaccination strategy is big, okay? It's not one. It's not all the individuals in the population taking the vaccine, but there is a huge proportion of individuals that take the vaccine, okay? But there is a region between these two boundaries, between the values that are not too big and not too small, where we have a third vaccination equilibrium. This is not an evolutionary stable vaccination equilibrium because the risk index function here is not strictly decreasing. On the other hand, it is increasing, okay? So we have this region where 3 different vaccination equilibria coexist. The lowest one, where nobody takes the vaccine, an intermediate value where some individuals take the vaccine, and this is only a Nash equilibrium, not an evolutionary stable vaccination equilibrium, and the biggest vaccination equilibrium, which is in the high vaccination scenario. Okay, so these are 3 different equilibriums that coexist for the same level of the relative risk. To finish, we use some ideas of the replicator dynamic theory. We create what we call the evolutionary vaccination dynamics, and the idea is the following. The individuals will change their vaccination strategies along time in such a way that their payoffs will increase. Okay, so we start to consider that all the individuals vaccinate with a certain probability P, and a small group of individuals, a certain group of size var epsilon, change from that strategy to a closed one. Okay, so we can compute the expected payoff for the individuals that do not change the strategy, the expected payoff for the individuals that change to a closed strategy. We divide this difference by the size of the change, basically. And if we take the limit when this size goes to 0, we obtain the dynamic evolution of the vaccination. Okay, we introduce here a different function, an alpha function that is positive, and it is 0 at the boundaries, just to make the dynamic bounded, basically. But since it is always positive, it measures the vaccination adaptation speed, how fast or how slow the people changed their vaccination strategy. Since it is positive, it's not interesting in a dynamical point of view. To find the dynamic evolution of the morbidity relative risk, we simply consider this difference function. Okay, psi is the same thing, it's positive, so it's not important. But the difference between the vaccination strategy P and a certain threshold value is what makes the evolution of the relative risks. Okay, and the motivation to consider this difference is simply this: if the vaccination levels in the population are greater than a certain level that we consider here as PT, okay, if the vaccination levels are greater than this threshold value, there are small levels of infection because there will be many people taking the vaccine. And if there are small levels of infection, people are less afraid of becoming infected. The morbidity risks or the perceived risks of the infection will decrease. And they also believe that the vaccine is not necessary. The morbidity risks of the vaccine will increase. So the relative risk increases is what happens in this dynamic equation because the difference is positive. Okay, so we have finally a two-equation system to study. It's a very simple ODE system to analyze. And we start by observing that the equilibrium points are the vaccination Nash strategies, okay? Are the threshold values, the PT values that puts the risk index equal to the relative risk, so are the vaccination Nash strategies. For small basic reproductive ratios, once more, the first case, the positive Nash equilibrium, the positive vaccination Nash equilibrium are the attractors of the dynamics, okay, are also the equilibrium points of this two-equation system, but are the attractors, okay. The most interesting thing happens for large basic reproductive ratios, okay. In this case, the high vaccination scenario, the evolutionary stable vaccination strategies corresponding to high levels of vaccination are also the equilibrium points of the dynamic and are also the attractors, okay? But if we decrease our threshold value, and if we decrease below this maximum point of the risk index function, then the Nash equilibrium are not attractors of the dynamic, are unstable points, okay? And if this threshold value crosses the maximum point, we observe an up bifurcation, okay? We have a pair of eigenvalues that cross the imaginary axis, and we obtain an unstable equilibrium point and a periodic orbit around that unstable point. Okay, this periodic orbits corresponds to what we call the vaccination cycles. Okay, and are quite important because we can say things like this, we can conclude things like this. If we have small levels of vaccination in the population, then to put more people vaccinating, the relative risk must decrease. Okay, it's only this way, decreasing the relative risk, that people will vaccinate more. Okay, to decrease the relative risk, we can use, or it may be necessary, vaccination campaigns or different things, but it's only this way, decreasing the relative risk, that will put people vaccinating more. Okay, in a similar way, if the vaccination levels are high, people will perceive a higher relative risk, and then the vaccination levels will decrease again. Okay, this is our main result, our main figure, and I will finish here. Thank you for your attention, for your presence. I don't know if there are questions now.
Well, in the interest of time, I will pass directly to my talk, but thank you, José Martins, for your quite nice presentation. So,
thank you.
If you can close the screen sharing, please. Yes, thank you. So I'll start with mine right now. So I'll be talking about a dynamical model using game theory that makes the interconnection between democracy and corruption. So this is the outline of my talk, and I'll begin with some motivation in the introduction. Well, nowadays, when we started this model, it was perhaps not in Portugal, not as in the news as it is today, but corruption has been for a long time one of the topics that is commonly on the news and is a matter of concern. And it affects, and it's studied, it affects several areas of the society, and it's studied by several branches of science. And particularly today, public awareness is increasing, but even in 2014, when the European Union made the seminal anti-corruption report, all over the European Union, 76% of the citizens consider that corruption is widespread. And in Portugal, the number was around 90%. Corruption has a direct and indirect costs. As for direct monetary costs, in the same report that I talked before, they say that bribery, embezzlement, financial and tax fraud, money laundering, cronyism, and so on, cost the European Union economy around 120 billion euros per year, which is just a little less than the annual budget of the European Union. Of course, it's quite smaller than the gross domestic product, but if you think about that amount of money, that really has an impact on society. And when you look at public contracts, again in the same report, the increased cost due to corruption in public contracts are on average around 20 to 25%, and there are cases that the increased costs reach nearly 50%. So it's a high burden on the public expenditure when you look at things this way. But besides direct monetary costs, there are also indirect costs. So there are several studies that look at the empirical and theoretical that bring up empirical and theoretical evidence showing that high and rising corruption increases income inequality and poverty, and this has an impact on the society, and it undermines democracy because people may start to believe that their leaders are not defending them as they should. So corruption can be defined as the misuse of public power for private benefit. Looking at the paper by Jane from 2001, he suggested the following types of corruption. So grand corruption involving political elites, bureaucratic corrupt practices involving appointing bureaucrats or officials that deal more directly with citizens, and corrupt acts when they meet the public, saying accepting a bribe to make easier for the citizen a given subject that he wants to be solved. And there is also legislative corruption when voting behavior and policy making the legislator when voting behavior and policy making of the legislator is influenced by private interests and lobbying. So these are the main sets that we are looking at. In our model, we'll consider three types of agents, again, according to Jane. So we consider the government, officials, and the citizens. The government or the political elite has two pure strategies, to be corrupt or not. And the officials or bureaucrats also have two pure strategies, to be corrupt or not. And the citizens also have two pure strategies, in this case, to be compliant with corruption or not to be compliant with corruption. Looking at the citizens, being compliant or non-compliant can have several interpretations. We'll interpret in the following two ways: the compliance with corruption. They may comply with corruption because they support it. For instance, if they receive some benefit, so like vote buying, they receive some money or some goods to vote for the one in the government that is offering their goods. Or they might receive a different benefit, not so direct, but say a new street in their area of residence or something like that. And then there is also the non-supporting corruption. And in this case, we have citizens that do not like corruption, but since corruption might be infiltrated in several sectors of the society, they have to play the rules of the game, even if they don't like it. And whenever they have the opportunity to vote for in a democratic regime, they will vote against those that they feel that are corrupt. So this is the citizens, and we can construct a payoff table regarding the interactions of the citizens on the left and the four types of pure strategies that we can observe from the government and the officials. So this -1 is a normalized payment, and this is a disutility that the citizens have when they meet a corrupt official. So this -1, we can think it's a bribery or something like that. UO is in here and in here is the extra disutility or dissatisfaction that a non-compliant citizen faces when he meets a corrupt official, meaning that they have to pay the bribery, but they feel some discomfort, for instance, and so this would be an abstract cost, or they decide to make a complaint, and this will be, say, the legal costs in the court that they have to pay. We also have UC, which is the externality that the compliant citizens receive that is transferred by the government. Say, you vote buying, favoritism, clientelism, cronyism, or propaganda, among other mechanisms. So propaganda will mean that the government is advertising that that country is wonderful, and people start believing if the propaganda is effective, meaning that they will be happier living in those conditions. And finally, we have UG and UG bar, which is the externality that the non-compliant citizens get when the judiciary system works well and they fight corruption through that means, and moral social beliefs that these non-compliant citizens feel when they are against corruption, feeling that they are doing the correct thing. And UG bar is the extra utility of the citizens that they get by not having to be compliant with the corrupt government. So this would be theoretically the ideal case. When you look at the officials, they can also be corrupt or non-corrupt. Being non-corrupt, it means that they perform their task according to the law and the regulations. They do it honestly. Corrupt officials try to seek an extra benefit from an advantage position that they have, and either directly to themselves or helping a third party that they are interested on, like a family member or a company. We also have a payoff matrix for the officials. The value F is the fine that the officials will have to pay to the government for being corrupt. The value 1 is the bribery or the utility that they receive from citizens. PO is the utility transferred to the government to keep their corrupt behavior. It can be some sort of payment or bribery or fines or something like that. And PO bar is the utility transferred from the non-corrupt officials to a corrupt government because they have to keep their jobs, or because they have their life harder. It's the same thing. So let's say that a non-corrupt official facing a corrupt government might have difficulties in promoting and stuff like that. In that case, it will be a negative, like a disutility, as is presented on this payoff matrix. And finally, the government can also be corrupt or non-corrupt. A non-corrupt government will be seen by the citizens as a guardian against corruption, and in these actions, through these actions, the citizens will have a positive opinion and will have the tendency to vote for them. A corrupt government will support corruptions and will benefit from payments or bribes to maintain this behavior. So looking at the government payoff, we have VC, is the extra voting externality attributed to a non-corrupt government for its re-election by the compliant citizens, meaning that the compliant citizens will vote and will give some utility to the government, to a non-corrupt government to be kept in functions. And the compliant citizens, in some sense, might be more aware of the corruption because they will deal it actively on their daily lives. We also have VC bar, which is the extra voting externality attributed to a non-corrupt government for its re-election by the non-compliant citizens. So they are less aware of the corruption because they do not have to deal with it in their daily lives, but they also favor non-corrupt government. And when we compare these two values, if the compliant citizens are not aligned and oppose corruption, then we can have VC bigger than VC bar. If vote buying or other practices of the government favor the compliant citizens, then we can have the opposite inequality. So regarding the other terms in the government payoff, we have the J term, which is the extra cost with maintenance and efficiency of the judiciary system, meaning that courts have to work, investigation has to work to fight corruption, and that has a cost in terms of the government. And we also have this L value, which is a loss that a corrupt government incurs to increase its chances of remaining in power. So this might mean vote buying or propaganda or stuff like that to keep themselves in power. Our model will be based on replicator dynamics. So these first two terms will be such that all dynamics works in the unit cube, and we have a difference in the expectation of the utility when compared one's pure strategy with the other pure strategy. So what we are looking at here is we have three variables, one for the government, one for the official, and one for the citizens, and each variable will code the probability of each agent to play the corrupt or non-corrupt strategy in the government and the official's case, or the compliant or non-compliant strategy in the citizen's case. So we look at the EF case, meaning that G is for the corrupt strategy of the government, O is for the corrupt strategy of the officials, and C is for the corrupt is for the compliance strategy of the citizens, all of them meaning probability, which means that we are allowing the agents to play in a mixed strategy case. So we can rewrite those equations with the expected values, these terms in brackets, as a linear combination of the probabilities of the officials, the citizens, and the government being corrupt or non-corrupt, or being corrupt, or the citizens being compliant, where these letters are given by the parameters of the model. And when we look at the dynamics, all we need to check is if that term in brackets will be positive or negative, because the term to the left will also be always positive. In particular, when we look at the edges of this unit cube where all the dynamics lie, along one edge, we have two of the coordinates fixed and only one of the coordinate is not fixed. So let's say that this black axis, all we need to know when you look at the sign of the derivative is, in this case, the value of the parameter dg. If it's positive, it means that we'll go from this point to 0, 0, 0, meaning that everyone behaves correctly towards this point, and in our coordinates, this will mean that the government will increase its corruption. If we look at different edges, we'll have different dynamics depending on if the signs are positive or negative, and this is just one example of the set of signs that we can choose. So this is what I just said, and if we solve the system, we can. It is possible to have an interior mixed equilibrium. If it exists inside the unit cube, it lies in this set of values, and furthermore, we can also obtain the Jacobian matrix of the equilibrium, and with that, building the characteristic polynomial, which is given in here, we can study the stability of the equilibria. And since this is a cubic polynomial with real coefficients, there is a real root, and applying Vieta's formulas, we see that the sum of the three roots of the polynomial is 0. And so this means that we have two cases. The first case is a degenerate case when one of the roots is 0. The second case, we don't have that degenerate case, and 0 is not a root. And since the sum of the roots is 0, it means that the real part of one root, of at least one root, has to be positive, and the real part of at least one root has to be negative. And since they sum to 0, it means that we either have a positive root and two negative and two roots with negative real part that are complex conjugate, or we just switch signs and we have one negative root, one with 0 imaginary part, and two positive roots that are complex and have opposite imaginary values. So, looking at this model, we can have several cases, and we'll start by showing, and I will present two examples in this presentation. One of them is the bistable equilibrium. In this case, for the parameters values that we've chosen, we have an interior mixed equilibrium, and we also have the vertices are equilibrium, but only two of them are stable equilibrium: the 0, 0, 0 and the 1, 1, 1. The 0, 0, 0, it's the ideal case where the government is not corrupt, the officials are not corrupt, and the citizens are not compliant with corruption. So that is the ideal case. The other stable equilibrium will be the 1, 1, 1, meaning that the government is corrupt, the officials are corrupt, and the citizens are compliant with corruption. So this is the worst of the cases. And the mixed equilibrium belongs to a stable manifold, which is two-dimensional, and the boundary is one repelling heteroclinic cycle. And we can have some conditions to have this this non-corruption attractor and then the corruption attractor, meaning that the utility of the government through vote externality is high enough than the gains with the corruption action. So meaning that the government will value more the voting of the citizens than the gains that they have with corruption. The officials are also non-corrupt because fines are high enough to deter them from being corrupt. And citizens are non-compliant because in the absence of corruption by the government and the officials, there is no point in comply with something that do not exist. The corruption attractor is stable if something else occurs. So we have different set of inequalities. And in this case, it is stable if the gains with the corruption action of the government are high enough to support vote buying from the compliant citizens and being re-elected. And also, this is enough to be supported by the fines to the low fines to the corrupt officials and the low judiciary costs. So that would be a way of getting this equilibrium. Regarding the officials, they are corrupt because the gains with the corrupt acts are large enough to overcome the utility transferred to the corrupt government, and the citizens are compliant because the utility transferred from the corrupt government, for instance, through vote buying, is high enough to overcome the briberies that they have to pay and the effort that they would have to go through to fight corruption. I will also present briefly a second case where we have an attracting sixth-edge heteroclinic cycle. So in this case, we also have a mixed equilibria in the middle, and the mixed equilibria belongs to a surface that is an attracting that is an unstable surface to the mixed equilibrium that is attracting into that is attracting one direction and repelling in two directions. So we again have inequalities, and the inequalities what will give us is the trajectory. So if we start from the 0, 0, 0 corner, the government will become corrupt if the gains from corruption are high enough to overcome the eventual costs that they have through the loss of voting from the citizens. And as we move along this direction, the officials, we don't see a very large difference in their behavior because the fines are still quite high for them to change their behavior. When we go through this second axis, the officials are becoming corrupt because now, after the government is corrupt, the fines are no longer that high, and so they will benefit from corruption. And citizens will not comply with corruption yet, because as we move along this line, they still have to make an effort if they comply. So they still have a cost if they comply with corruption that they are not wishing to have. As we move along this axis towards the bad equilibrium, the 1-1-1 equilibrium, citizens are becoming compliant because both government and the officials are now corrupt. And so what we see is that their costs are now high enough if they try to fight corruption, and so they decide to be compliant with it. And the government will not change its strategy as we go up because they still do not perceive enough loss in the votes from the citizens, and so they decide that to keep their corrupt behavior. Now that many citizens, or at least all of them in the extreme case, are compliant, since in this model they do not like corruption, although they comply with it because they feel that they have no other option, whenever they have the possibility, they will vote for another government. The government feeling this will start being non-corrupt and will start to take measures to to fight corruption. So the government will move along this direction, and the officials will still be corrupt because they will feel that they do not have an advantage if they stop being corrupt. So the advantage is higher if they are corrupt. And then in the fifth step, we move along this line. The officials stop being corrupt because the fines now are high enough, and the citizens keep their strategy because it's still hard to not comply with corruption, so they decide to comply with the corruptions from the officials. And in the final step, we move back to the initial equilibrium, completing our heteroclinic cycle, and the citizens become non-compliant because now we have no corrupt government and no corrupt officials, meaning that it makes no sense for the citizens to be compliant with something that do not exist. And as we move along this line, the government keeps being non-corrupt because the voting externality that they are getting from the citizens, from the non-compliant citizens, is high enough to overcome the possible benefits of being corrupt. So this is one example of an attracting heteroclinic cycles. There are other cases with different parameters, but this is the diversity of the model that we have. So we introduced a game theoretic model for corruption in a democratic state. We have an evolutionary dynamical model, and there are several possibilities in this dynamic, a bistable equilibrium, either one extreme or the other, or a heteroclinic corruption cycle that is a global attractor. Of course, this model, being simple as it is, in particular, the expected values are linear, means that we are getting extreme cases in terms of the trajectories. So the heteroclinic cycle moves along the edges of the unit cube. So a more realistic model will have trajectories inside of the unit cube, but qualitatively is something that we may observe in societies, periods with higher corruption than periods with lower corruption, not as extreme as in this model, but qualitative. We are looking at something that is observed in societies. So this ends my talk. Thank you for your presence in this session. Thank you for I also thank the organizers for all the work that they have been with this conference. And if you have any questions, I can also answer if you wish. So I'm not seeing any questions. Since we are in the end of our scheduled time, if we don't have questions, I'll just thank all the participants once again, and thank the organization once again. And I wish you a good reminder of the day in this national encounter and in this conference. So thank you all.
Hi, Bruno. Bye, all.
Bye, José, Filipe, and João Paulo. See you soon. Thank you, Adelia, for all the support in the beginning of the session, and also the other organizers that I don't see the name because it only says live 3 streaming. So
thank you.
Goodbye.
Bye-bye.
Goodbye.